So, let us now discuss another numerical method which is called Gaussian quadrature. In deriving trapezoidal rule and Simpson's rule, we observed that trapezoidal rule involved function evaluation at 2 points. So, there are 2 ordinates which have to be computed, and the method is exact for polynomial of degree up to 1. So, you took 2 points and the method is exact for polynomials of degree up to 1. In the case of Simpson's rule, it involves evaluation of function at 3 points. So, 3 ordinates have to be obtained, and the method is exact for polynomials of degree less than or equal to 2. In addition, we know that these methods have been derived using equally spaced points, and we observe that the Newton-Cotes methods which are derived with equally spaced points are such that if you are given information at n plus 1 points, then you are able to obtain an integration method involving n ordinates, and the method is exact for polynomials of degree less than or equal to n. So, one wanted to see, can one derive an integration method such that the method is exact for polynomials of degree greater than n. Gauss said that yes, it is possible if one is ready to sacrifice the requirement that the nodes must be equally spaced. So, if you sacrifice the requirement that the nodes within that interval must be equally spaced, it is possible for you to construct an integration method such that the method is exact for polynomials of degree greater than n. So, he said that one can obtain integration methods of the form integral a to b f of x dx, which is of the form sigma, say k is equal to 1 to n c k f of x k. So, k runs from 1 to n. So, there are n unknown constants c k, which are C1, C2, etc., Cn. In addition, we have xk's which are also not known to us. So, x1, x2, etc., xk, that is k running from 1 to n, they are the nodes that we have to select in that interval a to b, which need not be equally spaced. So, that we have another n unknowns. So, totally we have 2n unknowns to be determined such that sigma k equal to 1 to n c k f of x k will evaluate this integral, and the method will be exact for polynomials of degree less than or equal to 2n minus 1. So, how many ordinates that you use in this method? There are only n ordinates. The ordinates are at x1, x2, etc., xn. So, you involve only information about the function at n nodes. Evaluation involves only n ordinates, but the method that you derive is such that it is exact for polynomials of degree less than or equal to 2n minus 1. Say for example, if n is equal to 2, then you will derive a method which is exact for polynomials of degree less than or equal to 2 into 2 minus 1, namely less than or equal to 3. you will see that the xi's which are located here need not be equally spaced. So, let us work out the details proposed by Gauss and arrive at a Gauss quadrature, say for the case when n is equal to 2. So, we require an integral of the form a to b f of x dx is sigma c1 f of x1 plus c2 f of x2. You do not know c1, c2, you also do not know x1, x2, but the method must be exact for polynomials of degree less than or equal to 2 into 2 minus 1, namely less than or equal to 3. So, this requires the knowledge of the properties of Legendre polynomials. So, we briefly present those results and use them in the derivation of Gaussian quadrature methods. So, what are Legendre polynomials? The Legendre polynomials are solutions of the Legendre equation, Legendre differential equation, which is 1 minus x square into y double prime minus 2x into y prime plus n into n plus 1 into y equal to 0, where n is an integer. And solutions are given by Rodrigues formula. So, you must have derived these in your course on differential equation when you studied about special functions. So, Rodrigues formula tells you that the solution of this equation y of x, which is a Legendre polynomial of degree n when n appears here in the differential equation in the form n into n plus 1, then the solution is given by 1 by 2 power n into n factorial into nth derivative of x square minus 1 to the power of n. So, when n is 0, you get the Legendre polynomial of degree 0, which is 1, and when n is 1, from here you will obtain that it is x. P2 of x will be half of 3x square minus x, 3x square minus 1, and P3 of x will be half of 5x cubed minus 3x, and so on. You can get higher degree polynomials, and you observe that polynomials with suffix odd are odd polynomials, odd degree polynomials, and those denoted by with even suffixes are even degree polynomials. In addition, the polynomials have the property that Pn at 1 is equal to 1. You can check P2 at 1 is 2 by 2, P3 at 1 is again 1, and so on. So, they satisfy the property that Pn at 1 is 1. Further, they satisfy an important property which is called an orthogonality property, which says integral minus 1 to 1 Pn of x into Pm of x dx is 0 whenever the polynomials are of different degree, and it is 2 by 2n plus 1 when they have the same degree. And these polynomials are such that if you consider minus 1 to 1 Pn of x into x to the power of m dx, that will be 0 when m is less than n. Further, the roots of these polynomials or zeros of these polynomials are the roots of Pn of x is equal to 0 lie within the interval minus 1 to 1. So, these are some properties which we require in deriving Gaussian quadrature formulas. So, we have recalled these results. So, let us now work out the details of Gauss quadrature method, say when n is equal to 2 in this formula. So, let n be equal to 2 in star. So, since I know that the Legendre polynomials are such that the roots of the Legendre polynomials Pn of x is equal to 0 lie within the interval minus 1 to 1, Gaussian integration methods have been derived for integral minus 1 to 1 f of x dx. So, we seek an integration method such that integral minus 1 to 1 f of x dx is sigma k is equal to 1 to n c k f of x k. So, you may ask me, then how do you get, if you are asked to evaluate an integral of the form integral a to b f of x dx? We will illustrate it. We simply have to use a transformation or change of variable such that the integral between a to b goes to integral between minus 1 to 1. So, we shall discuss that later. Let us now derive the integration method when n is equal to 2. So, we require a method such that integral minus 1 to 1 f of x dx is sigma k equal to 1 to 2 c k f of x k. So, namely c1 into f of x1 plus c2 into f of x2. So, find c1, c2, x1, x2 such that this integration method, let us call this as double star, such that double star is exact for polynomials of degree n is 2. The method says for polynomials of degree less than or equal to 2n minus 1. So, here we determine these unknowns in such a way that the method is exact for polynomials of degree less than or equal to 2 into 2 minus 1, namely 3. So, we know how to work out the details. So, we take f of x to be equal to, therefore, 1, 2, 1 x, x square and x cubed, and substitute in double star and then see how you can make use of the properties of the Legendre polynomials and evaluate this integral. So, when I take f of x to be 1, then I get it is x between minus 1 and 1. So, that is 2, and that will be equal to c1 into f of x1 which is 1 plus c2 which is f of x2. Then integral minus 1 to 1 x dx is x square by 2 between minus 1 and 1, and that will be 0, and that will give you c1 into f of x1 is x1 plus c2 into f of x2 is x2. Then integral minus 1 to 1 x square dx will be x cube by 3 between minus 1 and 1. So, that will give you 2 by 3 into c1 into x1 square plus c2 into x2 square. Then minus 1 to 1 x cube dx will be x to the power of 4 by 4 between minus 1 and 1, and that again will be 0, and that is equal to C1 into x1 cubed plus C2 into x2 cubed. So, we observe that we have 4 equations to determine the 4 unknowns C1, C2, x1 and x2. So, at this stage we would like to bring in the knowledge of Legendre polynomials that we have and use their properties. So, what I do is, suppose I call these equations as 1, 2, 3, 4. I shall multiply equation 3 by 3 by 2. So, you will understand why we do this. So, multiply equation 3 by 3 by 2 and equation 1 by half and resulting equation 3 minus 1 gives the following. So, let us write minus 1 to 1, 3 by 2 x square, that is the left hand side. Then I have to subtract half times the first equation. So, integral minus 1 to 1 half. So, integration with respect to x. And what does that give? That gives you, from here I multiplied the equation 3 by 3 by 2, I mean equation 3 by 3 by 2. So, I have 3 by 2 into C1 x1 square plus 3 by 2 C2 x2 square, and I subtracted half times the first equation. So, half C1 minus half C2. So, the left hand side is minus 1 to 1 half of 3x square minus 1 dx, and the right hand side gives me C1 by 2 into 3x1 square minus 1. So, I have taken these two terms plus C2 by 2 into 3x2 square minus 1. So, now it must be clear to you what is it that we have here. We have integral minus 1 to 1 p 2 of x dx is equal to C1 into, what is half of 3x1 square minus 1? It is p2 at x1 plus C2 times again it is p2 at x2. We have integral minus 1 to 1 p2 of x dx as C1 p2 of x1 plus C2 p2 of x2. The left hand side is integral minus 1 to 1 p2 of x dx, which is p2 of x into p naught of x dx, and that is 0 by orthogonality property of Legendre polynomials. So, this will be C1 p2 of x1 plus C2 p2 of x2. This gives therefore C1 p2 of x1 plus C2 p2 of x2 is 0. Let us now derive another equation. Suppose I multiply equation 4 by 3 by 2 and equation 2 by minus half and add the two equations. then we get integral minus 1 to 1 3 by 2 x cubed minus half x into dx is C1 into 3 by 2 into x1 cubed minus C1 into half x1 plus C2 into 3 by 2 x2 cubed minus C2 into half x2. This gives C1 into x1 into 3 by 2 x1 square minus half plus C2 into x2 into 3 by 2 x2 square minus half, which is C1 x1 into half of 3 x1 square minus 1, that is P2 of x1 plus C2 into x2 into half of 3 x2 square minus 1, which is P2 of x2. Now, let us look at the left hand side. So, we have left hand side as integral minus 1 to 1 x into half of 3x square minus 1 integrated with respect to x, and that is integral minus 1 to 1 p1 of x into p2 of x dx, which is again by the orthogonality property of the Legendre polynomials 0. Thus, we have the second equation to be given by C1 into x1 into P2 of x1 plus C2 into x2 into P2 of x2 is 0. So, let us call these equations as 5 and 6. Now, looking at equations 5 and 6, we observe that these two equations are identically satisfied for any choice of the constants C1 and C2 if we choose x1 and x2 to be the zeros of P2, namely the Legendre polynomial of degree 2. In which case P2 of x1 is 0, P2 of x2 is 0, and therefore, this equation will be identically satisfied and this will also be identically satisfied, and for any arbitrary choice of C1, C2, equations 5 and 6 will be satisfied. So, therefore, for any arbitrary choice of C1 and C2, the equations 5 and 6 will be identically satisfied if x1 and x2 are chosen as zeros of P2, namely the zeros of half of 3x square minus 1 equal to 0. This is P2 of x. So, if I consider the roots of this equation, which are zeros of P2, then they will identically satisfy equation 5 and 6. So, what are the zeros? They are given by x is equal to plus or minus 1 by root 3. So, we integrate between the limits minus 1 and 1. and the roots of P2 of x is equal to 0 are given by x1 is equal to minus 1 by root 3 and x2 is equal to plus 1 by root 3. So, these two nodes lie in the interval minus 1 to 1 and they are located symmetrically about the origin, and both these nodes are interior points. They lie within the interval minus 1 to 1. So, we have determined x1 and x2. The only problem that remains to be solved is determine the constants C1 and C2. So, we consider the first two equations, namely C1 plus C2 is equal to 2, C1 x1 plus C2 x2 equal to 0. These are the first two equations which we had written down. Now that I have determined x1 and x2, it is C1 into minus 1 by root 3 plus C2 into plus 1 by root 3 and that is 0, which shows that C1 is equal to C2. So, substitute here, that will give you 2 C1 is C2. So, C1 is 1, but C1 is C2. So, C1 equal to C2 equal to 1, and therefore, we have the integration method to be given by integral minus 1 to 1 f of x dx is equal to C1 f of x1 plus C2 f of x2. C1 is 1, x1 is minus 1 by root 3, C2 is 1 and x2 is plus 1 by root 3. So, knowing the function f of x, which is the integrand in the given integral, you evaluate f at minus 1 by root 3 and at plus 1 by root 3, then the sum of these values will give an approximation to this integral, and the method is exact for polynomials of degree less than or equal to 2n minus 1, where n is 2 here, namely for polynomials of degree less than or equal to 3. So, this method is exact for polynomials of degree less than or equal to 3. There are only two nodes at which the function is evaluated. The method is exact for polynomials of degree less than or equal to 3. As we remarked earlier, the two nodes lie within the interval, they are interior nodes, and the method does not involve the function evaluation at the end points of the interval, and therefore, these methods are referred to as open type formulas, which give you integration methods for evaluating a definite integral of the form minus 1 to 1 f of x dx. The Newton-Cotes methods that we had discussed earlier, for example, the trapezoidal rule, Simpson's rule, they both involved the ordinates or the function values at the end points of the interval. They are referred to as closed type formulas, whereas Gaussian quadrature methods are open type formulas, since they do not involve function evaluation at the end points of the interval. So, we have derived 2-point Gaussian integration method given by this, which requires the knowledge of roots of Legendre second degree polynomial. So, that once we know the function which has to be integrated between minus 1 and 1, evaluate this function at these two zeros of P2 or roots of the equation P2 of x is equal to 0, and that will immediately give you the value of this definite integral. So, usually we will be given an integral of the form integral a to b f of x dx, and we will be asked to evaluate this integral. Suppose say we are asked to evaluate such an integral using Gaussian quadrature method, namely use 2-point Gaussian quadrature technique to evaluate this integral. We observe that we have derived this method where an integral of the form integral minus 1 to 1 f of x dx is expressed as f at minus 1 by root 3 plus f at 1 by root 3. But the given problem involves limits as a and b, where a and b need not be minus 1 and 1 respectively. So, we have to convert this integral a to b f of x dx to an integral of the form integral minus 1 to 1 f of x dx. So, we consider a transformation which converts integral between a and b to an integral between minus 1 and 1. So, let us see how we can do this. So, let us consider integral a to b f of x dx. So, I would like to convert this integral to the form integral minus 1 to 1, say f of x dx, and then evaluate it using Gaussian quadrature. So, we make use of this transformation. X is b minus a by 2 into x plus b plus a by 2. Let us see whether it works. So, when x takes the lower limit value a, then we have a equal to b minus a by 2 into x plus b plus a by 2. So, we have a minus b plus a by 2 is b minus a by 2 into x. So, we have a minus a by 2 minus b by 2, which is minus of b minus a by 2, and that is minus b minus a minus, that is b minus a by 2 into x, which tells that x takes the value minus 1. So, when capital X is a, small x takes the value minus 1. What happens when x takes the value b? That gives you b minus b plus a by 2 is b minus a by 2 into x. So, b minus b by 2 is b by 2 minus a by 2, that is the left hand side, and the right hand side is b minus a by 2 into x. So, that shows that x takes the value 1. So, therefore, when capital X varies between a and b, small x varies between minus 1 and 1, and therefore, this integral a to b f of x dx will be equal to, under this transformation, minus 1 to 1 f of, what is capital X? Capital X is b minus a by 2 into small x plus b plus a by 2. And what is d capital X? So, d capital X from here is b minus a by 2 into dx. So, b minus a by 2 into d small x. So, if I have integral a to b f of capital X dx, it is b minus a by 2 integral minus 1 to 1 f evaluated at this node into dx. So, suppose say I apply Gaussian quadrature with n is equal to 2 and evaluate this integral. What is it? B minus a by 2 into minus 1 to 1 f of this integration with respect to x. So, that gives you, you should take the node at minus 1 by root 3. So, at x is equal to minus 1 by root 3, the function must be evaluated. So, that gives you this function evaluated at b minus a by 2 into minus 1 by root 3 plus b plus a by 2, that is the first term. And then the next term will be f evaluated at 1 by root 3. So, b minus a by 2 into 1 by root 3 plus b plus a by 2. That is going to be the second term. So, this integral has been evaluated using Gaussian quadrature. You know a, b, etc., because the upper and the lower limits are known, and therefore, substitute those values, and this will give you the value of this integral between a and b. So, let us take an example and illustrate this. Evaluate integral minus 1 to 1, or let us do for a general integral of the form a to b. So, integral 2 to 3 cos 2x by 1 plus sin 2 x, sin x, integration with respect to x. Using Gauss quadrature method with n is equal to 2. So, we call this as Gauss 2-point quadrature formula. So, evaluate this integral using Gauss 2-point integration method. So, we write down the transformation. X is b minus a. So, a is 2, b is 3. So, b minus a, so 1 by 2 into x plus b plus a, so 2 plus 3, so 5 by 2. So, this is the transformation, and dx is half d small x. So, by that formula, integral 2 to 3 cos 2x by 1 plus sin x dx will be integral minus 1 to 1 f of, isn't it, cos 2, what is x? X by 2 plus 5 by 2 divided by 1 plus sin of x by 2 plus 5 by 2 into d capital X, that is half of dx. So, now we would like to evaluate this using 2-point integration method. So, what does it say? This simply says get the function value at x is equal to minus 1 by root 3. So, the integral will give you half of cos of x, which is minus 1 by root 3 divided by 1 plus sin of x at x is equal to minus 1 by root 3. So, minus 1 by 2 root 3 plus 5 by 2. So, we have evaluated f at minus 1 by root 3. Then the second term at x is equal to 1 by root 3, this should be evaluated. So, cos of x is 1 by root 3 plus 5 by 2 divided by 1 plus sin of 1 by root 3 plus 5 by 2. So, both the ordinates have been computed, and this gives you the value of the integral. So, you can use your calculator and then show that it is equal to half of 0.56558356 minus 0.15856672, and when you simplify, you get the result as 0.2035082. So, using 2-point integration method, we have been able to evaluate this integral. Let us take another example. So, evaluate integral 0 to 1 f of x dx, where f of x is 1 by 1 plus x. So, the interval a to b is now 0 to 1. So, I have to make a transformation so that this integral is converted to an integral of the form minus 1 to 1, in order that I am able to apply Gauss 2-point integration method. So, I make the transformation x is equal to b minus a by 2 into t plus b plus a by 2. What is b? 1, a is 0. So, 1 plus 0 by 2. So, it is t by 2 plus half. So, that dx is half dt. So, what is the value of this integral? It is half integral minus 1 to 1, right. Dx is half dt divided by 1 plus what is x? T by 2 plus half. So, it is half of integral minus 1 to 1 dt by 3 by 2 plus t by 2. So, what is my function? My function here is f of t, and that is 1 by 3 by 2 or 3 plus t by 2 or 2 by 3 plus t, that is my f of t. So, this integral, if I call this say as I, then the integral I will be half of f evaluated at minus 1 by root 3 plus f evaluated at plus 1 by root 3. That is Gauss 2-point method. So, that will give you half of, we know what the function is, 2 by 3 plus t is minus 1 by root 3 plus 2 by 3 plus t is plus 1 by root 3. So, simplify this and write down what the value of the integral is. So, the natural interest is to see what happens if you increase this n. Namely, immediate curiosity is to see what is going to be Gauss 3-point integration quadrature method. So, we shall derive Gauss 3-point integration method in the next lecture. Thank you.